Welcome to Pre-Calculus. Today we will investigate finding real zeros of polynomial functions, focusing on the connection between zeros or x-intercepts of a graph and linear factors of a function's equation. We'll take a look at one example. Here our instructions are to graph the function by creating a table of at least 5 coordinate points. So we'll start by graphing. And then once we've got that table in the graph, we want to use it to write the factored form of the polynomial function, noting any multiplicities. Well, let's start with that first task of graphing the function. So we'll set up our table and we'll put our x column and just put -2, -1, 0, 1, and 2. Always a good place to start. Then we want to calculate our f of x or our y values, and we'll do that. One way we could do it is by plugging it into the function. So that's -x cubed plus x squared plus x minus 1. So I'm going to choose to go to the graphing calculator because I want to see some stuff there in addition to just grabbing a table of values. So I'm going to head over to desmos.com. And I'm going to start by just inputting that function. So that's f of x again equals -x to the power of 3 plus x to the power of 2 plus linear x minus constant 1. And I can see my graph there. It's showing the characteristics I would expect. I've got a degree 3 function, so it's got one arm up, one arm down, and it's a negative leading coefficient, so the left arm's up, right arm's down. What I want to do is get a table of values, and what I'm on the lookout for when I get that table of values is really what are the x-intercepts or the zeros. So I can see here, and it lines up with what I'm seeing in the graph, that I've got a 0 or an x-intercept at -1. You always can tell because the y value is 0 in that right column. I've got a second 0 at positive 1. So that's another 0 there in the y column. So that's going to help me to graph. I do want to catch one other point. So remember, you always want to find the coordinates of the minima or maxima. So this left-hand minima, if I click there, I can see why it's not shown up in the table. It's negative point repeating 3. So -1/3 for the x value. Those decimal values never show up in a table with integers. And its y value is -1.185. So I do want to grab any extreme points, minima or maxima. And I'm good on the maxima on the right-hand side because that's actually at 1, 0. In fact, we'll need to use the fact that it hits the x-axis there and bounces back to help us with our second task. But let's graph this first. So I'm taking those 5 points from the table and the 6th point, which is my relative minimum there. And I'm going to go back to the notes screen to record that. I'll fit in that point for the minimum first. So negative point repeating 3. That had the output of -1.185. And then I'll fit in all the rest of these y values. So -2 had a y value of 9. -1 was a 0. The y-intercept is -1. So 0, -1, 1, 0. That's my other 0, and 2, -3. So to finish that first task, I'm going to just plot these points and graph. So I do need to add a line here for 9. There's -2, 9. -1, 0. The minimum is at -1/3, -1.1. So I got to just estimate both of those x and y values. 0 is at -1, so we can see the function rising up a little bit. At 1, 0 hits the x-axis, then it bounces off again to -3. So I want to sketch that function. It descends on the left there, hits the minimum, rises up, hits the x-axis, bounces off, and descends down to negative infinity. So there's my graph, and that completes that first task. So my second task is to use the table and the graph to write the factored form of each polynomial function, and being on the lookout for any multiplicities. So what we do to find any linear factors of the polynomial function is I'm going to look at those places in my table and on my graph where I had x-intercepts. So I'm going to color code here. The green one is the same on the table and the graph. And I'll also highlight this second one on the table and in the graph. So I notice that I've got two different kinds of zeros. The one that I've highlighted in green represents the function crossing through the x-axis. So notice it on the left there at that green highlighted point, the function is starting from above, passes through the x-axis, and has negative y values. So what that would give me is one linear factor when it passes through. I'm going to write that here, and then we'll work on actually writing the linear factor. One linear factor when the function passes through the x-axis. So I'm just going to make a note there that that zero occurs at the x value of -1. We'll use that in a moment to write that linear factor. Well, let's take a look at the second group here. So the second one that I've highlighted here in turquoise, notice how it's different in its behavior on the graph and in the table from that one on the left, the one highlighted in green. The one in turquoise, the function doesn't actually pass across the x-axis. So for this function, it approaches -1 and hits the x-axis, doesn't cross through it, but bounces back down. Anytime you have a maximum or a minimum that's on the x-axis like that, so for me, the best word is a bounce. That indicates that what I've got there is a doubled factor. So let me write it here in general terms, and then we'll say, how does that show up as factors for our function here? So if I've got a bounce, I'll put that in quotation marks because that's an informal term, bounce on the x-axis, which in math language would be a maximum or a minimum with the vertex on the x-axis. What that signifies are two linear factors that are identical, two identical linear factors. So we got two different types of x-intercepts or zeros here. What we want to do now is, now that I've kind of seen the characteristics of each, I want to take and use those descriptions to write the linear factors. So what I've done in the light blue here is I've just written it out, what is the x value when the y value is 0. And what I want to do is I want to then solve this so that the right side is 0. It's very easy to do. All we got to do is add 1 to this first expression, that little equation, and that would give me this x plus 1 equals 0. So you just solve it so that it equals 0. And what that gives me is one linear factor of my original f of x. So what I'm going to do is I'm going to start writing this in its factored form. So I see I've got that 1 on the left-hand side where the graph passes through the x-axis at -1. When I solve that for 0, it gives me this linear factor of x plus 1. So notice the sign flipped. So when I go down to solve the second zero that I saw here, where x equals positive 1, I would subtract 1, and that would give me another linear factor of x minus 1. Now, I'm leaving space there because, again, that right-hand 0, where the graph hits the x-axis and then bounces off of it without passing through it, the space is for a duplicated factor there. And that's true anytime you see a polynomial function that does that at a 0, where it hits the x-axis and bounces back, doesn't actually cross through. And what I would do is I would go ahead and write that x minus 1 duplicated. So I'm running into my table there, but that's the factored form for this function, x plus 1 times x minus 1 times x minus 1. And notice that we got those factors from our graph and our table just by looking at where does the graph cross the x-axis. A last thing that I need to note is that this had a negative leading coefficient. And so what I have to do is I've got to supply that myself out here front. So the last thing you want to do is make sure that the leading coefficient matches the original. And I'm going to box that. So its factored form should be negative parentheses x plus 1 parentheses x minus 1 parentheses x minus 1. And I'd like to prove in a second that that is actually the same function. Before we head off, though, what I want to notice is this duplicated factor, because the last piece in our instructions here says to find any multiplicities. So if I've got a duplicated factor there, one thing that I could say is that this is a factor x minus 1 multiplicity 2. Multiplicity is a fancy way of saying how many times does that factor occur in that factored form. So this is a multiplicity 2. So on your work, when you get that factored form and if you see a doubled or a tripled factor, in this case I had 2 of them, so I'm saying it's a multiplicity of 2. Well, let's take this back to Desmos just to prove that they are the same function. And it's a good way that you can use to check your own work as you're creating the factored forms. So let me demonstrate how to check that. So I'm going back to Desmos. I haven't taken that original standard form function out. All I'm going to do is type g of x. And then I'm going to type what we had gotten for our factored form. So negative parentheses x plus 1. Close parentheses, x minus 1, close parentheses, x minus 1. So you see that duplicated one. And what was our curve in black, that's how Desmos was presenting f of x there. It's presenting our g of x here in a burnt orange color. They are the same function. So a good way to check is to leave your original function in and then type your factored version. See if it lands exactly on top of the original. If it does so, you can be pretty confident that they are in fact the exact same function. Thank you for joining for this investigation of finding real zeros of polynomial functions. I'm going to let you go work and graph and find the linear factors and zeros of your own polynomial functions. Thank you for joining. See you soon.